Hi, AP Chemistry. Welcome back to talking about applications of acids and bases. Last time we talked, we looked at buffers and we looked at what happens to a buffering solution when strong base is added to it. So we're going to continue talking about buffers just for a little bit today before we get into titration. But before we get going today, I just want to pause a little bit and take a look at Kw. So here we are mixing acids and bases, right? And as we mix acids and bases, there is a connection here to water, right? When you mix an acid and a base, it's called a neutralization reaction. And neutralization reactions make two things. One is water and one is a salt, right? Ultimately, acid-base reactions, most of them fall under the category of a double replacement reaction, right? You are basically switching ions, or you're taking two substances apart and kind of flipping the ions around and making two new things. And they always make water and salt. So there's a definite connection to water when you mix acids and bases. But there's kind of like an underlying connection to water also. So in order to see this, I want to look at Kw. Now remember, Kw is a very specific law of mass action equation that relates to a very specific reaction. So before we go any farther, take a minute, see if you can write that reaction and the Kw equation. Now would be a good time to pause. Okay, so remember, Kw is describing this autoionization reaction of water, where two water molecules collide, and once in a great while, one of the waters can knock off a hydrogen from the other water and claim it. So what you're going to make is H3O plus and OH minus. Okay, so the Kw is going to describe that reaction. We'll have H3O plus here, we'll have OH minus here, and then we ignore water because water's a liquid, right? We can ignore anything that's a water, that's a liquid or a solid. All right, so that's Kw. Now I want to show you the connection between that and acids and bases. So I'm going to pick an acid. Let's go HCl. Go ahead and write out the HCl reaction and the Ka that's associated with it. So pause the video here and do that. So here's my reaction of an acid reacting with water. And the associated Ka is going to be products raised to their coefficients over reactants raised to their coefficients, ignoring anything that's a liquid or a solid. So we ignore water here. Okay, I'm going to do the same thing now for the conjugate of that. So if we look at hydrochloric acid's conjugate, which is Cl minus can technically act as a base. Now we know it's a weaker base than water, so we would classify it as a useless base, right? But we can still write the reaction as if it were going to act like a base. So again, third time, go ahead, pause the video here, write the reaction for the chloride ion in water acting as a base and the associated Kb. All right, so there's my reaction. My Kb equation is going to be products over reactants, ignoring anything that's a solid and a liquid. Okay, so here's where the interesting stuff starts. All right, let's take a look and see what happens when you multiply Ka and Kb. So go ahead, pause the video, write that out, cancel anything, any species that are going to reduce themselves out. So simplify your equation and see what you get. All right, I'm just rewriting Ka. All right, now I'm going to rewrite Kb. Oh, I probably should have kept those colors consistent. Let's do that real fast. Now I'm going to rewrite Kb. Okay, now I'm going to take a look and reduce out anything that appears in the top and the bottom. So HCl over HCl is going to reduce to 1. Cl minus over Cl minus will reduce to 1. And what I'm left with is that. So H3O plus times OH minus. And notice what that is. That is Kw. And so that's why Ka times Kb is going to equal Kw. Now we have used that, but we've never talked about why that equation works. Here you go. If you take an acid and multiply it by its conjugate base, right? You take your acid's reaction, write out the Ka equation, take your conjugate base, write that out, write its Kb equation out there. You multiply Ka times Kb, and they're very close to being inverses of each other, with the exception of H3O plus, the hydronium ion, and the hydroxide ion, right? And what you're left with is the hydronium times hydroxide, which is Kw. So the Ka times the Kb for any given acid and its conjugate base, or any given base and its conjugate acid, is going to equal Kw. So this becomes another tool for us. We know what Kw is at 25 degrees Celsius. It's always very consistent. And so if we're given the Ka of 1, we can find the Kb. If we're given the Kb of 1, we can find the Ka as long as we are at 25 degrees Celsius. Okay, so this is a tool that you're going to use, especially as we move forward into mixing acids and bases. Put this one in your back pocket, and let's continue to talk about buffers. Okay, so we talked about buffers, and we talked about how they work conceptually. Now I want to show you the math behind that explanation, right? So buffered solutions are solutions where you have both an acid and its conjugate base present, or a base and its conjugate acid present. And so the power of having a solution like this is when you put in a strong acid or a strong base, hydroxide or hydronium ions are not allowed to accumulate. And that's what changes a pH, right? A pH is a direct measurement of the amount of hydronium ions that are present. So if they're not allowed to accumulate, then your pH is going to stay very constant. Instead of accumulating, what happens is this relationship shifts. Acid is turned into conjugate base, or vice versa. Conjugate base is turned into acid. Since they're both present, it's a complete reaction that can shift the equilibrium between them. Now, mathematically, let's look at this a little bit more carefully. So this is a Ka equation just for a general acid, right? If we take any acid, we can write it as Ha, and we can write the generalized equation for that acid as such. And this would be the Ka for that acid reaction, right? Well, we can rearrange that Ka and solve for H plus. So we're going to take this A minus over HA, we'll multiply by the reciprocal, and we get this equation. So notice that this equation is going to explain some things that determine the H plus concentration. What is the H plus concentration of any given solution dependent on? Well, look at this. One of the things it's dependent on is HA. So if I asked you as chemists, what determines the pH of a solution, one of the things you should tell me is acid strength, right? The strength of an acid is going to play into this pH solution. If I have equal molar solutions of hydrochloric acid versus acetic acid, the hydrochloric acid is going to be at a lower pH because it's a stronger acid. Acid strength will play into the pH concentration of a solution, or the pH measurement of a solution. And here, mathematically, we see why. Because H plus concentration is dependent on the Ka. So if you use change the acid you're talking about and you change the Ka amount, or the Ka value, the Ka magnitude, rather, you're going to change the hydrogen concentration in solution. Mathematically, hydrogen concentration is dependent on the Ka. Hydrogen concentration is dependent on the strength of the acid. We also see a second thing here that hydrogen concentration is dependent on, and it's this ratio. Hydrogen concentration is dependent on the ratio of your acid and conjugate base that are present, or vice versa, your base and your conjugate acid that are present. That ratio affects your hydrogen concentration. So this is kind of the second thing. If I asked you what affects pH, the second thing you should have told me is concentration, right? The strength of the acid isn't going to be the only thing that's conveyed through that pH value. Concentration is also going to be communicated. And mathematically, here we see why, because that hydrogen concentration is tied to that HA over A minus ratio. When hydroxide or hydronium is added, the ratio shifts, right? We saw that we added 0.02 molar NaOH to 1 liter of solution, right? 1 liter of our buffered solution. And our pH did change slightly. I think it changed from 4.74 to 4.76, something like that, right? Because sodium hydroxide reacted with our acid was used, our conjugate base was formed, and this ratio shifted. Okay, so this is kind of a third thing that we can see as this ratio shifts in a buffer. The pH will change, but it will change in a small way, right? It'll change in a small way. Versus if we just added the hydroxide, sodium hydroxide, directly to the water, there would be no shifting of acid to conjugate base, right? And our pH would change dramatically. So when our pH changes, we're talking about one of two things. Either hydroxide or hydronium ions are accumulated and the pH changes in a big way. That is option number one. Option number two is that our ratio is going to shift, that hydroxide or hydronium concentration is absorbed and shifts this ratio, and our pH changes in a small way. So those are our two options of what this solution is going to do, and it depends on what's present, right? So notice down here, again, returning to this idea of like mathematically why buffered solutions work. So look down at the bottom of the page. Notice initially our ratio was 0.5 over 0.5, which was a 1. Once we added the sodium hydroxide and it was absorbed by the solution, it was consumed by the solution, and the solution shifted, we had a ratio of acid to conjugate base that was 0.96. So the ratio changed, therefore the pH changed, but it didn't change as drastically as it would have if those hydroxide ions were allowed to accumulate. Okay, so mathematically, this is your explanation as to why buffered solutions work. It comes down to this relationship, and so much can be explained through this relationship. You can explain why buffered solutions work. You can also explain what pH is dependent on, all coming back to this ratio, which is just, remember, a rearranged form of your Ka equation, of your law of mass action, right? Okay. Now, this becomes really useful. We can turn this into a very useful equation. So look at how this happens. Again, we have this relationship. It's our acid dissociation constant equation rearranged to solve for hydrogen concentration, right? If we take the negative log of both sides, negative log of H plus becomes pH, negative log of Ka becomes pKa, negative log of this ratio, this should be a negative log of this ratio becomes positive log of the inverse ratio. So look at this equation now. This equation is going to be mind-blowingly useful. Okay, you may have just toned me out. I have a very relaxing voice as I talk about math equations, right? I will put you to sleep at night. However, wake up. This equation is mind-blowingly useful. I'm going to show you why in just a second, but you got to believe me, it's going to allow you to skip half the problem if you understand this relationship. Notice, you can calculate pH as long as you know the pKa and the ratio of your conjugate, of your acid and its conjugate base. So this equation can only be used under certain circumstances, right? What kind of a solution do you have to have in order to use this equation to calculate pH? You must have both the acid and conjugate base present. If you don't have the acid and conjugate base present, you cannot use this equation. If you have the acid and conjugate base present, you have a buffer. So this equation is for buffers only because it only works if you have the acid and conjugate base present. If one of those is missing, you cannot use this equation. That's worth writing down and boxing and starring with your glitter pens, right? Okay, so this equation is called, it has a name, as all most important equations to us do. This is called the Henderson-Hasselbalch equation. I'm not really sure how to spell Hasselbalch, something like that. It's the Henderson-Hasselbalch equation. It can be used to solve for pH only as long as you are trying to describe a buffered solution. Now, this equation reminds me a lot, not conceptually, but mathematically, it reminds me a whole lot of M1V1. Okay, M1V1 equation can save you a lot of work, but you have to know when you can use it and when you can't use it, right? M1V1 does not apply to every single solution. In fact, it only describes can be applied to specific solutions when they're undergoing specific changes, also known as dilutions, right? If you're not dealing with a dilution, you cannot use this equation. So it's a really helpful equation when you can use it in the right context. But a lot of students don't understand that context and they just kind of blanket apply it to everything, and it doesn't work. It misleads you, right? Henderson-Hasselbalch's the same way. You can only apply it to specific solutions. When you have those solutions, it's really easy to use. It saves you a ton of work. But if you apply it to the wrong solution, it's going to mislead you. It's not going to work at all, right? And you may not know that it doesn't work. Okay, so make sure you know the context in which you can use Henderson-Hasselbalch. Now, let me show you this equation, how to use it, and why it's so useful. All right, so for example, we're going to figure out the pH of the following solutions. Okay, so let's take this first solution here and figure out the pH of it. Now, we're going to do this the old way, right? Where we A, write a reaction, B, write our ice chart, C, use our Ka equation. So we're going to do this. We look at the things we have present. We think about what they're actually going to exist as in solution. My weak acid will largely stay together. My soluble salt will largely fall apart. So I am going to have these three substances present, plus water always. Now I look at these and I consider which ones are going to influence pH. I have a weak acid. I have a useless acid. I have a weak base. And then my weak acid and weak base will both be stronger than water. So when I write a reaction, when I care about pH, that's what we're trying to solve, right? What is the pH? Okay, I have to use the things that are going to affect pH, which is my weak acid, weak base. Okay, so now that I know what I have, now I write my reaction. And I fill in my ice chart. Weak acids and weak bases. I don't know what the change is. I have to use X. I considered Q. Q is 0. I have to go towards reactants in order to, my equilibrium will go towards reactants in order to match my K equation. Okay, now I need to use my Ka in order to solve for X. Ka equals 1.8 times 10 to the negative fifth equals X times 3 plus X over 5 minus X. Okay, I'm going to ignore all the X's that are added or subtracted to numbers, and I get that. And now I can solve for my X. So I'm going to take my Ka. I'm going to multiply it by 5, divide by 3. X equals 3.0 times 10 to the negative 5. pH is negative log of that, which equals 4.52. Right? That's how we would do it. That's our normal process. Reaction, ice chart, Ka equation. Okay? Or I could take my information, and since I have both my acid and its conjugate base present, I can plug into Henderson-Hasselbalch. So instead of doing all of that, I could have just done this. pH equals negative log of my Ka, 1.8 times 10 to the negative fifth, plus log of conjugate base over weak acid. What is that? 3/5. There we go. All right, let's do this. Now, if I had a TI-83 with me, that's my goal this week. Go get one of those. I could do this all in one fell swoop. However, I'm working on my phone, so I cannot. There we go. Oh, no, that didn't work. Okay, I got 4.52. Look at that. They match. All right, so take a minute and reflect. Both processes work. Both processes get us to the pH of a solution that has both weak acid and its conjugate base present, right? But one of these processes is a lot shorter than the other process. So Henderson-Hasselbalch can be a really useful equation, but you have to use it in the right context. Okay, so now that we have a pH for our first thing, I want you to use either method. Find your pH of this second thing. Okay, now would be a good time to pause it and go find an answer. Okay, I'm going to do it both ways. And if you are uncomfortable with Henderson-Hasselbalch, remember you don't have to use it. You can find pH the normal way that we have been practicing for the last 2 or 3 chapters, right? And you will get the correct answer. Henderson-Hasselbalch is an optional shortcut, not a necessary equation. Okay, that would be the first way you set it up. Here's the second way. I ran out of room. And I'm doing conjugate acid over base, yep, in both cases. And then we calculate. And I get that answer for both of them. Okay, so again, hopefully you guys went one of the 2 ways, got the same pH. Now, just a moment here. Let's react or compare, reflect on our answers for the 2 solutions and draw a couple conclusions here. So notice I got the same pH for the first solution as I did for the second. Why? How are these solutions the same and how are they different? Well, they're different because the acetic acid and sodium acetate have different concentrations, right? In the first solution, it's 5 molar and 3 molar. In the second solution, it's 0.05 molar, 0.03 molar. Different concentrations, but same pH. Why? And hopefully what you see is it comes down to this ratio. Notice this ratio and our Ka affect our hydrogen concentration, which in turn affects our pH, right? Well, the Ka is the same for both of them because we're using the same acid conjugate base pair. And the ratio is the same for each of them. Also, 3/5 is the same ratio as 0.03 over 0.05. So ratio determines hydrogen concentration, right? That is our concentration tie-in. But notice it's the ratio that matters, not the actual concentration. Now, we're going to see here in just a couple slides that this ratio also determines buffer capacity. So does it matter if you create a buffer with 5 molar and 3 molar concentrations versus 0.05 and 0.03 molar concentrations? That's the question, right? Does it matter? Does it affect anything? Because if I'm in the chemical business and I'm selling buffers, heck, it would be a whole lot cheaper if I could make solutions with 0.05 molar and 0.03 molar, right? Those would be really excessively on the order of 100-fold cheaper solutions than creating 5 molar and 3 molar solutions. So does it make a difference? The answer in terms of pH is no, it doesn't. You're going to get the same pH of your solution either way. But in terms of capacity, yes, it matters. So that's where we're going next. We're going to look at buffer capacity and realize that although this ratio, as long as the ratio is consistent, our pH is going to be consistent. The magnitude of that ratio, the 3/5 versus 0.03 over 0.05, it does make a difference in terms of capacity. Okay, a couple other notes before we move on. Notice that we are using the initial concentrations. So when we are plugging into Henderson-Hasselbalch, notice we plug in initial concentrations because of the same approximation, right? X is going to be small. When I add that really small number to when I add or subtract it to another number like 3 or 0.03, and then I round off for significant figures, the X doesn't make a difference when it's added or subtracted. And so I round it off, and I end up using that approximation both when I use an ice chart and when I use Henderson-Hasselbalch. Same initial concentration approximation in both methods. Also, like we just talked about, the ratio and the Ka are going to determine your pH. So anything with the same ratio, the same Ka will come out with the same pH, but different buffer capacity. Okay. Lots of information on buffers. The more you deal with them, the more you calculate through with them, the more angles you see them from, the more people you have explain them to you, the more people you explain them to, the more you're going to understand them. Work with buffered solutions. Think through the solution as you work. Okay, so there's lots of examples here we're going to do together in class, and then you can do some work out of the back of your book. Also, make sure you are checking answers in the back of the book. Make sure you are asking questions when you get stuck. Okay, let's talk through buffer capacity now. So when we talk about capacity, if you think of like, okay, I'm going to go buy a bucket this weekend, and I want, if I tell you to go buy a bucket, say, I want a bucket, go buy me one. You're going to ask me, how big? Right? What you're really asking me is, what capacity bucket do you want? Do you want a little tiny decorative bucket that you can put a marble in? Or do you want a big giant bucket that you can collect rainwater in and store it over the summer, right? What capacity of a bucket do you want? So same thing with buffers. What is your buffering capacity? How much hydrogen and hydroxide can your buffer absorb, right? As soon as you use up all the conjugate acid or conjugate base, you have broken your buffer. So how much acid or base can a buffer absorb before it breaks, before you use up one of the two components? That is what we're talking about when we're talking about buffer capacity. So again, as we saw on the last slide, right? pH is going to be determined by the ratio of HA over A minus. It doesn't matter if this is 0.05 over 0.03 or if it's 5 over 3 molar, right? The ratio is all that matters for pH. But for the capacity, the magnitudes of your acid and of your conjugate base do matter. If I have 5 molar acid, if I have 5 moles in 1 liter, that weak acid can react with a lot more base than an acid that has 0.05, right? If I have a 5 molar acid, how much base can I add before that weak acid is used up? It's 5 molar, right? I can add up to 5 molar of that acid. Not the case for something that is 0.05 molar. How much base can I add here? Can I add 5 molar of my base? No, because you're going to use up all of this weak acid and you won't have weak acid left to absorb more base. So the magnitude of your concentration of weak acid conjugate base are going to determine how much base or acid that buffer can absorb. Okay, let's look at this. Let's calculate the change in pH that occurs when 0.01 mole of HCl is added to 1 liter of each of the following solutions. Okay, so we have solution A, solution B. So here we come back to the same type of question, right? What happens when we have a strong thing present with a weak thing, right? So first of all, we have to think, what's present and what's going to react together. So we have HCl, strong acid present. We have a weak acid present, and then we have sodium, which is going to be useless, and then we have acetate, which is going to be a weak base. So we have a strong acid, a weak acid, and a weak base present. And then, of course, we have water as well, but water is going to be weaker than our other things present. Okay, so now that we know what's present, what's going to react? Well, our strong acid drives the reaction. Anytime you have a strong something present, it's going to be your driving force. What is the strong acid going to react with? It's going to react with our weak base. So our reaction is going to be HCl. Now you can write HCl or you can just write H+. Remember, HCl is going to fall apart right away in solution into H+ and Cl-. So you can write H+ is going to react with C2H3O2- to form HC2H3O2. Okay, so there's our reaction. Now we consider our initial amounts. So we have 0.01 mole per 1 liter. 0.01 mole per 1 liter is going to be 0.01 molar. I'm going to change everything into molarity right away. All right. Now, again, I have 5 and 5 here. Now, can I plug this into Henderson-Hasselbalch? No, I cannot, because I don't just have weak acid conjugate base present. I have something else. I have hydrochloric acid. So because I have hydrochloric acid is going to drive this reaction to completion. Because it's a strong acid, I can't use Henderson-Hasselbalch. So my change is going to be all of my strong acid. Negative 0.01, negative 0.01, plus 0.01. I'm going to hit a final state here of 0.49.51. Okay, so my strong solution has driven it to completion. Now it's going to swing back to equilibrium. So here are my final amounts. These are not at equilibrium. It has to swing back to equilibrium. So now we need to figure out what we have at equilibrium. We have a weak acid and its conjugate base present. Can you use Henderson-Hasselbalch? Yes, you can. Okay, now I'm going to do this two different ways. Again, just so you see that doing Henderson-Hasselbalch is the exact same thing as not doing Henderson-Hasselbalch. So if you were to use Henderson-Hasselbalch, it'd be pH. You'd have to do the negative log of the Ka plus log of conjugate base over acid. Okay, so go ahead and figure out the pH in that scenario. And I'm going to set up an ice chart to show you can do it both ways. .51 initially, 0.49 initially, change equilibrium. It's a weak acid. My change is going to be X. Okay, I'm going to use my K equation. That's going to equal my Ka equation, which is going to also be equal to this, ignoring x's that are added or subtracted, and I solve for x and plug it into pH. Here we go. And it's acetic acid, so the Ka is the same. All right, so my pH is going to be 4.73. And you should have gotten the same pH, but a lot faster if you used Henderson-Hasselbalch. Okay, so how has the pH changed when that HCl was added? Well, it changed from, we never actually calculated the initial amount. Well, look at that. Okay, so the initial amount, the initial pH would be could be calculated using Henderson-Hasselbalch. Notice that the pH equals the pKa in this case, because my capacity is 5/5, which is 1. So log of 1 is 0, right? So what is my pKa? My pKa, which is equal to my pH, is 4.74. Okay, so my pH has changed from 4.74 to 4.73 in the case of the first one. So it's a change of minus 0.01 in terms of pH. What about the second one? Okay, so a good time to pause here, go through the process, see if you can get to the end with solution B. If you go through the same process, you can see I added it here in yellow. Same process, but with 0.05 molar for both species. You're going to get a pH of 4.56. Now, going from 4.74 to 4.56 is a bigger change, right? A much bigger change than with solution A. And you can see it's because the hydroxide reacted with a significant amount of my conjugate base and formed a significant amount of my weak acid. And so the ratio drastically changed. It's no longer 0.49 over 0.51. That ratio of A minus over HA is now 0.04 over 0.06. So because of our lowered buffer capacity, our additional acid had a greater impact on that ratio and therefore a greater impact on pH. So buffer capacity matters. With a smaller capacity, you're going to get more dramatic pH changes. You're also going to be able to break that buffer more easily. Notice in solution A, we would have had to add 5 moles of acid to that 1 liter. In solution B, we only have to add 0.05 moles of acid until that conjugate base is completely used up and gone, and we no longer have a buffer. So buffer capacity matters. It does make a difference. All right, so when we get back together, we'll practice some of this. And then we'll be ready to go into titrations. Woot! So let me know what questions you have. I will see you in class.